Total hip arthroplasty, otherwise known as a hip replacement surgery, is a common procedure with over 450,000 hip replacements performed in the United States each year. During total hip arthroplasty, a femoral head is inserted into the femur, while an acetabular cup is inserted into the pelvis to replace the hip joint. In some cases, where the bone quality is poor, like an osteoporotic bone screws are used to provide better stability for the acetabular cup. An issue that can still occur with bone screws being used to provide stability to the acetabular cup is that over time, different forces on the hip joint can cause the screw to be pulled and begin to toggle, leading to the screw failing. The goal of this project is to develop a bone screw optimized to improve purchase into osteoporotic bone. Some of the needs our team developed and focused on were the screw's ability to be easily inserted and removed from bone, the screw's stability in bone, and the ability to insert the screw with standard instrumentation. To approach the problem, our team focused on thread designs while keeping the screw length, shaft, and tip designs the same, while also modifying the screw head for testing purposes. Our team was able to develop 3 designs for initial testing, which were 3D printed by Exact Metal using a laser powder bed fusion printing process. The first test method our team used was an insertion torque test, where our team used a torque screwdriver to determine the minimum amount of torque needed to insert a screw into sawbone material that simulated osteoporotic bone. In addition to testing the screws our team designed, other screws with different thread designs that were made from common manufacturing methods for screws were also tested as controls to compare our screw thread designs. From the results of the insertion torque testing, it was found that our design had similar insertion torques compared to the control screws. The other method used to test the screw designs was an axial pull-out test. Screws were inserted into the sawbone material and then placed in an Instron machine to pull the screws out of the bone material. From the axial pull-out test, it was possible to determine the maximum pull-out strength of each screw we tested, where we found that our screw design was able to perform similarly to the control screws. Using the collected data, our team created a final prototype, leaving future steps being the manufacturing and testing of the final prototype.